Let us now look at how we will transform a three-phase waveform ABC to alpha beta coordinates, and from alpha beta coordinates to DQ coordinates, that is the DC coordinates. Now consider this three-phase waveform. Let me draw them. Now this is a three-phase waveform along the time axis: A phase, B phase, C phase, A phase, so on. So each is individually a time wave shape. Now this also can be represented in the spatial coordinates just like before. Now you can have three planes. A phase can be in one plane, let us say the horizontal plane. B phase can be at 120 degrees plane. C phase can be at another plane which is 240 degrees from the A plane. So their projections will be on the spatial coordinates, will look like this. So let us say I have three axes: A axis, B axis and C axis. They are distributed spatially 120 degrees apart, or 2 pi by 3 radians apart. Let me also draw the negative portions of the axis in a light color. B phase is 2 pi by 3 radians apart from A. C phase is 4 pi by 3 radians apart from A, all measured anti-clockwise. Now consider a reference line like this at a given time instant. Now at this instant, A phase is at a maximum, B phase and C phase are at negative 0.5. So I will put the A phase value. This is the A phase vector along the A phase line, because this is the projection along the A axis, horizontal axis, and that has a value 1. Let us say all these are sine waves of unit amplitude, so this has amplitude 1. Now the B phase and C phase both are at a meeting point here, and they are at amplitude 0.5. Now I will put, say, negative 0.5. So B phase axis is here, negative 0.5 is here, and C phase axis is here, negative C phase axis is on that side. So I will say C 0.5. Now these two contribute to the overall resultant vector. This is 60 degrees, this is 60 degrees, cos 60 is 0.5. So 0.5 into 0.5 is 1/4, 0.5 into 0.5, 1/4, 1/4 plus 1/4. So totally 0.5 gets added to 1. So you will have a total amplitude of 3 by 2, 1.5. So you will see a vector, resultant vector of 3 by 2 results if you have all unit signs. Now let's say these are the as an example, this could be phase voltage or phase currents. If you move this reference line along the time axis, smoothly along the time axis, this vector here will transcribe a smooth circle of amplitude of radius 3 by 2. So this is how it will come about. Just same like the two-phase system that we saw, alpha beta system. Now this three-phase system, we have to convert it into an alpha beta system. So you will get it into a two-phase system, orthogonal system, and from the alpha beta system, let us translate it into a rotating DQ reference frame. Observe that along this I have a resultant vector in this direction, and then let us say I shift the time, and at this point C is maximum, negative, so it is along this line. So it will be like this, the reference resultant vector. Then if I shift to another time, here B is maximum, B is along that one, so you will see the resultant goes in that fashion, and then negative A in this direction, the resultant. Then here C is maximum, you will see it is in this direction. Then here B is negative maximum, it is in this direction. And then A again, one cycle is complete. So you see the resultant vector makes a complete rotation. So it transcribes this circle in this manner. Now let me draw the alpha beta axis. Now I have the alpha beta axis. On that I will superpose the A, B, C axis, and let me take a vector RA, a vector RB and RC in this fashion. So this is just an arbitrary vector. So RA is along the A axis, RB is along the B axis, RC is along the C axis. Now our job is to convert the ABC vectors. This could represent IA, IB, IC or VA, VB, VC. So any arbitrary ABC vectors to alpha beta coordinate system. So ABC to alpha beta transformation. Let us do this. Now the vector R, which is a composition of RA, RB, RC. RA e to the power of j0 polar coordinates. RB is referred with respect to B axis, which is at angle 2 pi by 3. RB e to the power of j2 pi by 3. And RC referred to the C axis, which is RC e to the power of j4 pi by 3. So this is the vector, resultant vector R. Now expand that, you have RA plus RB cos 2 pi by 3 plus RC cos 4 pi by 3 plus J RB sine 2 pi by 3 plus RC sine 4 pi by 3. This is the imaginary part. Now put the values for the cos and the sines. RA minus RB by 2 minus RC by 2, because cos 2 pi by 3 is minus half, cos 4 pi by 3 is minus half. So this would be the real part, plus J RB into root 3 by 2, this is sine 2 pi by 3, minus RC root 3 by 2, sine 4 pi by 3 is minus root 3 by 2. So this will be the imaginary part. So this is of the form R alpha plus J R beta. So this will be R alpha, this will be R beta. Now let us represent this R alpha and R beta in a matrix form. So R alpha, R beta goes through a transformation matrix, which is now RA 1 minus half, this is minus half, and then for R beta there is no contribution from RA, that is 0, contribution from RB is root 3 by 2, contribution from RC minus root 3 by 2, and then you multiply it with this vector RA, RB, RC. So this is our transformation. So from this we see that we can get R alpha, R beta. So this is the vector R alpha beta, which is represented in the alpha beta coordinates, and the inputs are RA, RB, RC, and pass it through this transformation matrix, you will get R alpha, R beta in the alpha beta coordinate system. So this is ABC to alpha beta transformation. Now let us convert the alpha beta coordinate vector to dq. So alpha beta to dq transformation. dq is the synchronous reference frame which is rotating. Alpha beta is fixed, stationary. So let us say R dq we saw is equal to R alpha beta e to the power of minus j rho, where rho is the angle between the alpha beta coordinate and the dq coordinate system. So this is R alpha plus j R beta into cos rho minus j sin rho. So you expand that, you will see that you will get it in this fashion. Now this is RD and this is RQ. So that will be RD plus JRQ. So what is RD and RQ? I can put it in the matrix form. RD is this one. Cos rho will come in, sin rho will come in. RQ is minus sin rho and cos rho, and I can put in the input vectors, which is R alpha, R beta. So this thing has been put into this compact matrix form, and this will be the alpha beta to DQ transformation, and this is a vector, can say is in the DQ reference frame. So let us have a look at that DQ reference frame. This is the alpha and beta coordinate system. Let us take an arbitrary vector like that, and this red line is the D axis of the DQ reference frame. This is the Q axis, orthogonal, and the DQ axis is shifted from the alpha beta axis by an angle rho. If this angle rho is a varying angle, let us say it is varying at omega t, where omega represents the radiant frequency. So if it is rotating at 50 Hertz, then 2 pi 50 Hertz into t will be this angle, and this angle will be rotating, increasing at the 50 Hertz rate, and this DQ coordinate system is rotating. If this vector is representing current or voltage, again rotating at 50 Hertz, then this DQ reference frame will be synchronized with the voltage or current vector, and any projections onto the DQ axis reference frame will be constant, fixed, and they will be DC in this DQ coordinate system. Therefore, if you place the controller circuits and controller algorithms in the DQ reference frame, all the parameters will appear DC. So if I project this vector onto the DQ reference frame, RQ and RD, this relative values of RQ or RD will always be fixed. However, if this vector is projected with respect to the fixed alpha beta axis, now with respect to the alpha beta axis, this vector is rotating, this vector is moving, and therefore alpha value and beta value will change sinusoidally if it is a sinusoidal wave shape. And as this DQ reference frame is also rotating with the green vector here, RD and RQ will be constant, and so therefore in the DQ reference frame everything will appear DC. Now this is the concept. So this is how we have converted ABC sine waves, three-phase sine waves, into alpha beta two-phase rotating sine wave quantities, and from the alpha beta we have converted it into the DQ reference frame quantities, that is the RD RQ, which are DC in nature if you are sitting in the DQ reference frame and looking at the vector. We have discussed the three-phase ABC AC signals to alpha beta AC signals, and we have also discussed transforming alpha beta, that is the two-phase AC signals, to the DQ domain DQ DC signals. Now we should also be able to transform the reverse direction, DQ to alpha beta to ABC. So we will look at the reverse transformation. So first let us see how to go about doing DQ to alpha beta, that is DC domain to two-phase AC domain. We know that a vector in the alpha beta coordinate is given by vector in the DQ coordinate system multiplied by a transformation factor e to the power of j rho, where rho is the angle between the alpha beta coordinate system and the DQ coordinate system. This can be expanded as RD plus JRQ cos rho plus J sin rho, and expanding it further, you have RD cos rho minus RQ sin rho. This will be the real part, and the imaginary part RD sin rho plus RQ cos rho. So this will represent R alpha, this will represent R beta, and you can say R alpha plus JR beta. And therefore, in the matrix form, I can write R alpha R beta as follows. And RD cos rho, so cos rho will come in minus sin rho for the second term here, and for R beta I will put in sin rho and cos rho, and the vector input vector RD RQ. So knowing RD RQ, I can get R alpha R beta using this transformation matrix. So this will provide you with a vector representation in the alpha beta coordinate system, knowing the vector representation in the DQ coordinate system. You can visualize this. Let me draw the two coordinate system, alpha beta coordinate system, like this. So the alpha and the beta, and I will also draw the DQ axis. So this is the D and the orthogonal Q. Now the DQ coordinate system is displaced from the alpha beta coordinate system by an angle rho. This rho can be a varying rho. Let us say it is varying at rho equal to omega t at 50 Hertz frequency. Now consider that I have two vectors, one RD along the D axis as shown, and another RQ along the Q axis as shown. Now these two vectors RD and RQ can be composed, and you will get the resultant in this fashion. Now this resultant can be decomposed resolved along the alpha beta coordinate axis. So if you resolve it along the alpha axis, project the resultant onto the alpha axis, you will get R alpha. Project this along the beta axis, you will get R beta. So this R alpha R beta is what we want as the output, having RD and RQ as the input. So that is what this transformation has done. RD and RQ is the input. Knowing this, we will use this transformation and find out R alpha and R beta. For this, rho, the angle between the D and DQ coordinate system and the alpha beta coordinate system should be known. Now let us discuss how we transform a vector in the alpha beta coordinate to the three-phase ABC coordinate system. Now let us go by the graphical means. It is easier to understand. Let me draw these two orthogonal axes, alpha axis and the beta axis. I will also draw the ABC coordinate axis, the three axes which are displaced 120 degrees apart. So this is the A axis in line with the alpha axis. This is the B axis. This is the C axis. So the B axis is 120 degrees or 2 pi by 3 displaced from the A axis. C axis is 4 pi by 3 or 240 degrees displaced from the A axis. Now take an arbitrary vector, and this vector, let us resolve it along the alpha beta coordinates, and you have here alpha and beta as shown. Now let us say these vectors alpha, R alpha, R beta. Now these vectors have to be transformed into the ABC coordinate system, and they have to be converted into RA, RB and RC vectors along these three axes. So how do you shift R alpha, R beta to RA, RB, RC? So now let us take first RA. RA is a vector along A axis. Now what are the components of R beta and R alpha that are contributing to vectors along the A axis? R alpha is contributing completely because alpha and A are aligned. The beta axis is orthogonal to the alpha axis and therefore orthogonal to the A axis. There is no component of R beta along the A axis. Therefore, it is 0. So, component of beta is 0. So, RA is equal to R alpha. Now, what is the component along the B axis, RB? Now, R alpha component along the B axis. Now, let us say you project R alpha onto the B axis. So, this will be the projected value onto the B axis. So, now this component here, as I am showing in the cursor, will be the component contributed by R alpha by its projection onto the B axis. It is falling on the negative portion of the B axis. Now this angle is 60 degrees. How is it 60 degrees? You see that we know that B is displaced from the A axis. This angle is 120 degrees. Therefore, the remaining angle will be 60 degrees. So, therefore, I can say the contribution of R alpha minus, because it's on the minus axis, minus R alpha cos pi by 3 or cos 60. Now, if we take the R beta drop perpendicular to the B axis. So, this component will be the R beta component's projection on the B axis. It is on the positive side. So, you can write R beta, and this angle is 30 degrees because this overall is 120 degrees, B axis from A axis. Beta is at 90, so this will be 30. So that is cos pi by 6. So R alpha minus cos pi by 3 is minus half, pi by 3 is root 3 by 2. Now RC, what is the RC vector? So let us take the projection of R alpha onto the C axis. So this is the component, and this angle is 60 degrees. So R alpha cos pi by 3. Now this is falling on the negative part of the C axis, so therefore the minus. Then projection of R beta onto the C axis. This is the R beta component, and that is again falling on the negative part of the axis, minus R beta cos of pi by 6, because this portion is 30 degrees. So now when you put the values for cos pi by 3 and cos pi by 6, you get R alpha minus 1 by 2 plus R beta into minus root 3 by 2. Now there is another important point that you have to note. Remember that while we converted or while we transformed the vectors from the ABC to alpha beta, and when the ABC amplitudes, or let us say unit amplitudes, that is the sine waves, the three 120 degree phase shifted sine waves RA, RB, RC are having unit amplitudes, then the amplitude that resulted was 3 by 2 in the alpha beta domain. So we have to make, when you do the reverse transformation, when you are having a value 1 in the alpha beta domain, it will be 2 by 3 in the ABC domain. So to make that correction, you can multiply each of the vectors by 2 by 3, because now R alpha, if it is 1 amplitude, and it multiplied by 2 by 3. So each of them is multiplied by 2 by 3 to bring in that factor of 3 by 2, which which comes in when you are transforming from ABC to alpha beta domain because of the algebraic addition. A unit sign will become 3 by 2 amplitude sign in the alpha beta coordinate system. Likewise, when you do the reverse transformation, a unit sign in the alpha beta coordinate system will become 2 by 3 times the amplitude in the ABC coordinate system. So now when you put it into the matrix form, so what I need is RA, RB, RC. And what is the transformation matrix? You can look at it. Now R alpha into 2 by 3. So I will put 2 by 3. R beta component 0. Now minus 1 by 2 into 2 by 3 will be minus 1 by 3. And root 3 by 2 into 2 by 3 will be 1 by root 3. This will be minus 1 by 3 and minus 1 by root 3. So this gets multiplied by alpha and beta. So this will be our transformation matrix for converting a vector in the alpha beta coordinates. The resolved components R alpha and R beta can be converted into the three-phase AC quantities RA, RB, RC using this transformation matrix. So now summarizing, you can say first we know how to do ABC to alpha beta transformation. ABC is three-phase AC sign. Alpha beta is two-phase AC wave shapes. So three-phase AC to two-phase AC transformation. Next, alpha beta to DQ. So what do we do? Alpha beta is two-phase AC. DQ is rotating along with the vector, keeping in pace with the vectors. Therefore, the vectors projected on the DQ coordinate system will appear DC. So it becomes two-phase DC domain. So this is the forward transformation. Can also have the reverse transformation, DQ to alpha beta. The DQ to alpha beta, the DC quantities in the DQ coordinate system get converted to two-phase AC quantities in the alpha beta coordinate system. So it is a two-phase DC to two-phase AC transformation. Now the fourth one is from alpha beta to ABC. That's what we just last did. Alpha beta is two-phase AC to three-phase AC. So if you take a set of variables, signals, let us say sinusoidal signal, three-phase sinusoidal signals 120 degrees apart, you can go through the whole process of going to two-phase to DC, and then DC to two-phase AC to three-phase AC back by using these transformations.